Chapter 1.11.4 Logging Architecture. Summary. Logging helps track events in applications, especially for troubleshooting. Modern apps and containers utilize logging but need extra support for complete logging solutions. Cluster-level logging ensures logs maintain independent storage and lifecycle within a Kubernetes setup. Multiple third-party solutions are available to handle and store logs effectively. Kubernetes logging architecture supports log management, from simple node logging to advanced solutions like sidecar containers. It doesn't cover direct app log pushing. Logging architecture. Logs are crucial for tracking app behavior and fixing issues. Container engines aid in logging but aren't a full solution. Logs must be recorded independently in clusters. This concept is cluster-level logging needing separate backend systems. Kubernetes lacks built-in log storage. Other tools are necessary. These sections explain log management on nodes. Pod and container logs. This code snippet is a YAML configuration for a pod named counter, with a container named count, using the BusyBox 1.28 image. The container runs a shell script that continuously outputs the current date and time every second. The code is using the kubectl apply command to apply the configuration defined in the counterpod YAML file, which is hosted on the k8s.io website. This command will create a pod named counter, running the BusyBox 1.28 image that continuously outputs the current date and time every second. The code shows the output of creating a pod named counter, using the specified YAML configuration file. The message, pod, counter created, indicates that the pod creation was successful in the Kubernetes cluster. The code, kubectl logs counter, is a command line instruction for the Kubernetes control tool, kubectl, to display the logs of the pod named counter. It retrieves and displays the logs generated by the container running within the counter pod. The code snippet shows the output of the logs from the counter pod with timestamps in UTC for 3 consecutive seconds. Each line displays the timestamp along with a counter value that increments every second, indicating a continuous logging operation. This command uses kubectl to retrieve the logs from the container named count, within the pod named counter. It specifies that only the logs from the specified container should be displayed. Kubernetes collects logs from each running container in a pod. Users run a pod using a specific manifest and utilize the kubectl logs command to access log data. If multiple containers exist in a pod, users must specify which container's logs they wish to view. Logs are handled by the container's runtime, which redirects any output to the application's stdout and stderr. While implementation may differ, the process is standardized as the CRI logging format. Logs remain even if a container restarts. If a pod gets evicted, all its containers and associated logs are removed. The kubelet manages these logs, accessible via the Kubernetes API. Users commonly access them using kubectl logs. In Kubernetes version 1.21, the kubelet rotates logs and manages how they are stored. 2 key settings include container log max size and container log max files, dictating the log file size and count respectively. They are set through the kubelet configuration file. Kubelet optimizes log rotation for clusters with high log output. It allows users to tune the number of concurrent log rotations and the frequency at which logs are monitored and rotated, configured through specific settings in the kubelet file. When users run kubectl logs, The kubelet reads from the latest log file only. This means if a pod generates significant log data, only the most recent logs are accessible. For example, from a 40 MB log, only 10 MB may be returned. System component logs. ### Types of system components. 1. * component categories. *. System components in Kubernetes are classified into those running within containers and those directly involved in running containers. Examples include kubelet and container runtime *. They operate outside containers. Kubelet's role *. It runs containers organized in units called pods. Scheduler, controller manager, and API server *. Typically run as static pods. 2. etcd and kube proxy *. etcd *. Operates within the control plane, often as a static pod. Kube proxy *. Normally runs as a daemon set in clusters using this component. ### logging mechanisms. 3. Linux log handling *. On Linux systems with systemd, kubelet and container runtimes log to journal which is accessed via journal.ctl. If systemd is absent, logs default to var log directories or can be redirected using kube log runner. 4. Windows log management *. Default log path is cvar logs, which differs from cvar log. Using kube log runner allows log redirection to preferred directories. ### storage considerations. 5. Persistent storage *. Kubernetes supports mapping persistent storage into containers running specific components. This ensures valuable data is maintained over time. ### log rotation and configuration. 6. Log rotation *. System components must have their logs shared in a way that facilitates rotation via parent node volumes. Log rotation may not be handled by Kubernetes, making it crucial to consider if tools account for rotating these logs or if manual setup is required. Adjustments in pod log paths should be cautious to prevent disruptions. Cluster-level logging architectures. The code snippet defines a pod named counter, with a container named count, that runs a loop to echo the current date and an incrementing value to two log files located in the var log directory. Additionally, the pod is configured to mount an empty dir volume at the var log path for storing the log files generated by the container. The code defines a Kubernetes pod named counter, with a container named count, running the busybox 1.28 image. The container runs a shell command in a loop, echoing incremented values along with the current date to two log files located at /var/log/1.log and /var/log/2.log. The pod also mounts an empty dir volume named varlog at var log for the container to write the log files to. Additionally, two other containers in the pod, countlog1 and countlog2, are configured to tail and follow the content of the respective log files in real time. The code kubectl logs counter countlog1 retrieves and displays the logs from the container named countlog1 within the counter pod. This command is useful for accessing specific container logs when a pod contains multiple containers. The code snippet shows a sample output of log entries with timestamps indicating when each entry was logged. The entries appear to be in sequential order, with each line containing the timestamp and corresponding log message. The ellipsis suggests that there are more log entries following the shown examples. This command uses kubectl to access and display the logs from the container named countlog2 within the pod named counter. The logs retrieved will show the output generated by the container, typically containing timestamps and any information written to the standard output stream. The code snippet shows logs written to a file /var/log/2.log every second with a timestamp and an info message followed by an incrementing index. The code snippet shows a config map named fluentedconfig, with data containing a configuration for Fluentd. It includes two source sections for tailing log files, 1.log and 2.log, and a match section for sending logs to Google Cloud. This code defines a Kubernetes pod named counter with two containers. The first container, named count, runs a busybox image and writes logs to /var/log/1.log and /var/log/2.log. The second container, named count agent, runs a Fluentd image with specific arguments and volume mounts for configuration. ***1. Node-level logging agent. Kubernetes lacks native cluster-level logging solutions, but using a node-level logging agent can help. This agent, typically a container, collects logs from application containers on the node and sends them to a backend. It runs as a daemon set, collecting stdout and stderr logs without altering applications. This method streamlines log aggregation. ***2. Utilizing sidecar containers. Sidecar containers help manage logs by writing to their dedicated stdout, stderr. This setup enables the separation of log streams from distinct application parts. The sidecar can also run a logging agent to capture logs from the application container. This ensures flexibility and minimal overhead while utilizing built-in tools like kubectl logs. ***3. Streaming sidecar approach. With this method, sidecar containers read application logs from files, sockets and print to their stdout, stderr. This allows for maintaining separate log streams, especially when applications don't support standard output. Different streams can be accessed using commands, and node-level agents automatically pick up these logs. ***4. Handling resource consumption. Streaming logs to stdout can increase storage needs. For single-file applications, it's advisable to write directly to dev stdout rather than a streaming sidecar. Sidecars also help rotate unrotatable logs, but direct use of stdout, stderr with kubelet is simpler for log rotation and retention. ***5. Sidecar with a logging agent. If node-level agents don't suffice, sidecar containers with specific logging agents like Fluentd can be used. While they cater to unique needs, they might consume higher resources and logs cannot be accessed using kubectl. Configuration involves setting up a config map and a volume mount for Fluentd. ***6. Direct application logging. While not inherently supported by Kubernetes, applications can expose or push logs directly. This approach, however, is considered outside Kubernetes' typical operational scope.